Okay, so let's look at this example where we're designing an open-topped box with a square base. So I'm going to draw the square base. And what we know if a base is square is that the sides are all the same length. So I'm going to call that length of the side x. You can call it whatever you like. It just needs to be the same letter on all of the sides because they are all the same. Then I'm going to draw the height of the box. And I don't really know exactly what the box looks like, but it doesn't really matter as long as I label things and I'm consistent. So I'm going to call h the height of the box. Now you're always going to be given a number. And then you have to figure out what is the formula that's equal to this number. So we have 32 cubic inches. So that's a volume. The volume of the box is 32 cubic inches. So then we need a formula for the volume. Well, for a rectangular solid, it's the length times the width times the height. So we would write that as x squared h, and now we know that has to equal 32. So we're going to hang on to this equation until later when we need it. So the equation with the number you'll use later. So then we need to maximize or minimize something. So read the problem carefully until you figure out what that is. And here we're asked to minimize the amount of materials. So I'm going to call the amount of materials M, or you could call it A, or whatever you like. And the amount of material is, if it was made out of cardboard, how much cardboard will it take to make it? So I have 4 vertical sides. So 4 vertical sides, and each of those sides is x by h. So I have 4xh for the sides plus x squared for the base, and then there's no top. If there was a top, we would need 2x squared, but there isn't. So now look at this equation, and this is what I want to minimize. It has 2 letters in it. That's a problem because we don't know how to do calculus with 2 letters. So we need to come back up to our equation with the number in it and use it to eliminate one of the letters. So you can solve this volume equation either for h or for x squared. If you solve it for x, it's going to be a lot more complicated. So I would solve it for h. You can do it either way, but that's how I would approach it. So if I want to solve for h, it means get h all by itself. So I divide both sides by x squared and get h equals 32 over x squared. So now I take 32 over x squared and I replace or substitute for the h in the equation, and that's going to give me a formula that has only x's in it. So I'm going to have 4 times x times 32 over x squared plus x squared. Now I have a function with x only, and I can do calculus with it. So let's simplify it a little. I have an x here and an x squared in the bottom. And I'm going to bring that x up and write it as x to the negative 1, so it will be easier to do my derivative. So now to find a minimum, I need to find the derivative and set it equal to 0. So I'm going to find the derivative. Going to have negative 128 x to the negative 2 plus 2x, and I'm going to set that equal to 0. Now there's lots of ways to go from here, If you happen to see multiply both sides by x squared, that's a good way. If you happen to see add 128x to the minus 2 to both sides. So I'm going to write it without a negative exponent because that's another reason why I have you write things without negative exponents, because I think it's easier to see what to do for algebra if you have positive exponents in denominators. So I'm going to add 128 over x squared to both sides. But like I said, there's more than one way to do this, so your way is fine as long as you could explain the algebra you're doing. So then I'll have 2x equals 128 over x squared. So then I can multiply both sides by x squared, because if you're trying to solve for a letter, you never want it in the denominator. That's not going to work well. So I'll have 2x cubed equals 128, divide both sides by 2, and get x cubed equals 64. So then you need to do the cube root of both sides. And remember, there's only one solution to a cube root, two solutions for a square root or fourth root. So x equals 4 might be the value we want. But this is not enough information to convince me that you have found the value of x that minimizes the amount of material. All you know at this point is that 4 makes the derivative 0. That's all you know. You need more information. So this is where the second derivative test comes in handy. So I'm going to do the second derivative. So the second derivative is going to be 256 x to the negative 3 plus 2. Okay, so then let's do our second derivative test, where we have an x value of 4 that makes the first derivative 0. And then I want to know what is the second derivative at that point. So I'm going to say, what is m double prime of 4? So it's 256 over 4 cubed plus 2. All I care about is whether this is positive or negative. I don't care what that number is. And I can just look at it and see everything there is positive and added. So this is going to be positive. So here's the scenario I have. The function is concave up. So the function is concave up. The first derivative is 0 here. M prime of 4 is 0, and I'm concave up. So when x equals 4, m has a local min. Now you've convinced me. Okay, so x equals 4. That's important to us. So let's go back up and look at our problem. So now I know x equals 4. And we're asked to find the dimensions of the box. So we need to also know what the h is. Fortunately, we have an equation right here that shows us what the h is. So h is 32 over x is 4, and we square it, so that's going to be 2. So h is 2. And the dimensions are in inches, since the volume was in cubic inches. So our answer is going to be 4 inches by 4 inches by 2 inches. So that's the dimensions of the box. Okay, then the next two examples are specially chosen to contrast with each other. And one of the big things we ask you to do over and over in college is look for what's same and what's different. So compare and contrast. Compare and see what do you see that's the same, and contrast and see what do you see that's different, and look for patterns. So these two problems, the first one, the number they give you is a length. In the second one, the number they give you is an area. Okay, so those are kind of the two different kinds of fence problems. And they're all variations on these two. So I'm showing you the basic two different types. Okay, so we have 1,200 feet of fencing. So we have this long piece of fencing that we can use. It's 1,200 meters long. Well, they're telling me they want to enclose a rectangular field bordering a river. And so the fourth side doesn't need fencing because it has the river there. So this first example walks you through the process step by step, and then the next one wants you to figure out how to apply that process. So this problem says let X represent the width of the field. So of this 1,200, we've taken up X and another X. So then it says write an expression for the length of the field. So the length is going to be 1,200 minus 2x, because that's how much is left after I bend up the two sides that are each a length of x. And if it's more helpful to see it on the picture like this, of that you bend up the two sides, and then 1,200 minus 2x is the length. Okay, then we're asked to find the area of the field. And the area is going to be length times width. But now we know the length is 1,200 minus 2x times the width of x. So now we have a function of x. I'm going to distribute because I'm going to do calculus in a minute. So 1,200x minus 2x squared. This is the area of the field. Okay, then C says find the value of x leading to the maximum area. So I know the area I want to find is a maximum, so I find the derivative, 1,200 minus 4x, and set it equal to 0 to look for any critical values. So 1,200 equals 4x, and x equals 300. That's my only critical value. So now let's look at the second derivative test. So I'll need the second derivative, and it's -4. So I really like the second derivative test on this problem because when I have an x value of 300, the first derivative is 0, and the second derivative is negative. I don't even have to do anything to notice that the second derivative is negative. It's always negative. So A is concave down here. So I'm at a spot where I'm concave down and the derivative is 0. So this must be a local max. So when x equals 300, A is maximized. Okay, so that was C. Find the value of X. That gives you a maximum area. Then D is find that maximum area. Well, we have an area equation that says A of X equals 1200X minus 2X squared. So let's put 300 into that equation. And I'm getting 180,000, and it's going to be meters squared. These real life problems have units attached to the numbers. So the answer, 180,000, is not going to be a complete answer. Okay, so one more time, the number that's given here is a length, and you're maximizing the area. Okay, so let's contrast that with this next example, that you're given an area and you want to minimize, least expensive. You want to minimize the cost. Okay, so this is the other type of problem with a rectangle and a fence around it. Lots of variations, but they're all similar to one or the other of these. So now we have a rectangular fence where we need the whole rectangle, and we're given a number. So the area equals 20,000. Well, we need a formula for the area. So we need to label the side lengths. So a rectangle is defined as 4 right angles, and then opposite sides are equal lengths. So I'm going to call the two shorter sides length X and the longer sides length Y. So my formula for area is length times width, or XY. So XY has to equal 20,000. And I'm going to come back and need this in a little bit, but I don't need it right now. So cost is what I want to minimize. So I need a cost function. It won't be of X at first. So I need a cost function. So we're given some more information in the problem that we haven't used yet. Fencing material costs $3 per foot for the sides facing north and south. So if it's $3 for each foot, and you have Y feet, then it's going to be 3Y dollars and 3Y dollars for those north and south sides. So that's going to be 3Y plus 3Y. And then the other two sides, the fencing material costs $6 for each foot. So I need to multiply by the X number of feet to get the total cost. So I'm going to have plus 6X plus 6X. So let's simplify that a little. We're going to have 6Y plus 12X. Then here's the part where I have a formula with 2 letters. I can't do calculus with 2 letters. I need to replace one of the letters using this formula I have with the numbers in it. So I can replace either the X or the Y, it doesn't matter. But just so we keep everything with X, which is the more familiar, let's replace the Y. So I need to solve for Y, and Y is going to equal 20,000 divided by X. So I'm going to take that 20,000 divided by X, replace Y with that quantity, and that's going to give me my function for cost that only has X in it. And then I know I'm going to do a derivative, so I'm going to clean this up a little bit to make it easier to do the derivative. So I'm going to have 120,000 x to the negative 1 plus 12x. So whatever you're trying to minimize or maximize, that's what you're going to find the derivative of. So c prime of x equals negative 120,000 x to the negative 2 plus 12, and I'm going to set that equal to 0. So I'm going to write this without negative exponent. And then I'm going to add 120,000 over x squared to both sides. So that'll give me 12 equals 120,000 over x squared. Multiply both sides by x squared so we can solve for it, because we can't solve for things in denominators. So I'm going to have 12x squared equals 120,000. And then let's get the x squared by itself. Divide both sides by 12. And get x squared equals 10,000. So technically, x equals plus or minus 100. But because this is a real problem, and x can't be a negative number, it's a length of fencing, we discard this negative, but we note that it makes no sense, so I don't use it for anything. But you note that it is a solution of the equation x squared equals 10,000. Okay, so this might be the x we want. But we need to do some more work before we decide if it really is for sure. So let's find our second derivative. Here's my first derivative. C double prime is going to be 240,000 x to the negative 3. Okay, so I just wanted to put that where I could see it. So let me bring it down here now. 240,000 x to the negative 3. So I'm going to write that over x cubed. Okay, so let's see what we know so far. When x is 100, we know c prime is 0 there. And then we want to know what c double prime of 100. Well, it's 240,000 over 100 cubed. And I don't care what the number is. All I care is it positive or negative? And it's clearly positive. So the second derivative is positive here. So that means the function is concave up. And if I'm concave up and the derivative is 0, now I can say when x equals 100, C has a local min. Okay, so that's hardly ever the final answer to the problem. So come back up to the problem and say we have x equals 100 is what we discovered so far. Sorry, it's 300, right? No, 100. Getting the two problems mixed up, sorry. So x equals 100. We're actually asked to find the cost of the least expensive fence. So we need to find C of 100. But we have a formula for doing that. It's 120,000 over x, which is 100, plus 12 times x, which is 100. So that's going to be 2,400, and this is dollars because it's the cost of the fence. So please study these two examples and make sure you see what's similar about them and what's different about them. A problem like one of these will be on the final exam.